welcome to Multivariable Calculus, or Multivariable Physics, Classical Mechanics, Episode 4. And today, in the actual physics portion, we're actually going to be talking about motion, specifically polar motion. So I'm going to talk a lot about... So the first thing I'm going to talk about is the motion in Cartesian coordinates. So equation of motion in that. So we know F. This is F of R, double dot, right? And R is simply our position. So this can be mapped into F of, M X M Y and M Z. Right. But today we're going to think about polar coordinates. So we're going to derive this equation for polar coordinates. And so to refresh your memory, we have Cartesian coordinates. And here we have our polar coordinates. We have an angle, a radius, and some angle. And so we define these in terms of this polar, and so these a radius and an angle instead of an x and a y, right? And obviously we have, since this angle is sort of crooked and rotated, then we need to look at the normal vector to the radius as the hat or as the unit vector for angle. Okay. So let's think about how do we transform between these two coordinate systems. Well, very easy. If we have an r, so we can go x is equal to r cosine theta, and then y is equal to r sine of theta, right? How can we transfer between both of these? Well, we can find the radius really easily. It's going to be square root x squared plus y squared. And then the angle, to find the angle, we want to do something. So we want to remember that tan of theta is equal to cosine theta or sine theta over r times r cosine theta, so which is y over x. And well, what does this give us? We can isolate theta by taking the arctangent of y over x, provided x is not equal to 0, of course, right? Which also, would put some restrictions on theta. You won't worry about that for now. So now that we have these, let's think of deriving our equations of motion. So we're going to start with our radius, and given some radius, well, we know we can break this down into r, which is its length r times r hat, right? That's the r vector. Here's r hat, and then has its magnitude. Because we know r hat is equal to r over r, right? Its magnitude. So what is the velocity? Well, velocity is going to be r dot, right? So that's going to be, well, that's just d over dt of r hat. But since this is a product, you take the product rule. So this becomes r dot times r hat plus r times r hat dot. And so this kind of becomes interesting. So what is this r hat dot that we're taking? So to find that, we're going to need to do another drawing. So I'm going to draw, this is going to be R1, and then in blue, draw R2. Here we have R change, some infinitesimally small change, dr, and then here I'm going to have d theta, and this is actually R hat. I'm sorry. Alright, so what can we do with this? Well, this tells us, or at least shows us that, and obviously this is in the direction of theta hat, right? This gives us this relationship here that the r hat is equal to the theta hat, right? And so from this we can obviously take, okay, it's theta dot times dt theta hat, and then if we want to, apply to both sides, we have r hat dot is equal to theta dot theta hat. And we can actually do the same for theta. So to do this, we need to draw some vector here, and I'm going to draw theta 1, theta 2, and I'm going to have this change, theta, d theta, and then this change in r. So obviously this is some vector r, then we have this change r hat, and this is the change in our angle times r hat. And obviously there's a direction here, so if you notice these are proportional. We just have to take the direction into account. So d theta hat is equal to the negative, because it's moving backwards. We have a backwards change in r, d theta times r hat. And through the exact same logic, we arrive to theta hat dot is equal to negative theta dot r hat. Okay, so this is going to be important when we actually apply this, because now we can apply this. So we get r dot r hat plus r theta dot theta hat. And this allows us to actually, we can split velocity into two components. So velocity r hat, right, plus velocity theta hat. Right, and so this velocity theta, if you're familiar, r theta dot, well, that's going to be omega, but we're not going to worry about that yet. What we actually want to do now is, now we found velocity, well, we know acceleration is equal to, velocity dot, which is equal to r double dot. So now we want to derive acceleration from velocity. So we take the derivative one more time of this expression, d over dt, so r double dot is equal to this, of r dot r hat plus r theta dot theta hat. And after we apply this, this is going to give us, it's just simple product rule, r double dot plus r dot r hat dot plus r dot theta theta hat plus r theta double dot theta hat plus r theta dot theta hat dot. Okay, so that's a lot. Now let's try to simplify this. Obviously we have our identities here we want to use. So this is going, we're going to add some corrections. So this is r dot theta hat, and then this is going to be this theta dot is going to turn into r, or negative r theta dot squared r hat. So putting all of this together, if you combining like terms, we end up with this expression r double dot minus r theta dot squared times r hat plus r theta double dot plus 2 r theta dot, or r dot theta hat, right? So this is our expression for acceleration in polar coordinates. And so what we can do, so we need one more thing here, and then that's this idea that we can split up our force into two components. So force r theta is equal to some force in the r, right, in the r direction, plus some force in theta in the theta direction, right? So applying this, well, we can essentially solve for f r theta by just putting these into the appropriate positions. So that be is m, so I'm going to put m on the outside. This is a vector, remember, vector function, and inside we have r double dot minus r theta dot squared, and then r theta double dot, those are two dots, plus 2r theta, and then these are dotted. Right, and so this is our expression for the equation of motion in polar coordinates. And actually, if you want to do it in cylindrical coordinates, we could do that as well. We simply add this z dot term towards the bottom, so then that would be f of rho theta, or not rho, r theta and z. It's going to be pretty much the exact same. So hope that made sense. Yeah, so probably look into, maybe do some examples with this. I'm going to, in the next episode, I'm going to look into momentum and mass. We're going to actually start working into angular motion. And then we're going to move on and then do actual stuff with this. So we're going to do air drag after that. So see you then.